Hi, this is Jinnai. I'm going to talk about MBR decoding. The title of the paper is Document Level Text Generation with MBR Decoding using Optimal Transport. And code is here, so if you are interested in, take a look at it. Okay, so what is the problem? So we are going to work on text generation problem. As many of you know, many NLP tasks involve text generation, like image captioning. Given an image, there's a probability model, often a language model, and the expected output is like a black cat or cat or face. And translation is similar. You get it on Chinese text, and the task is to translate it into English or whatever language we want. So these tasks you can think of generating a text given a context. So X is a context, and H here is the output. So traditionally, all like many of the people are working on beam search to text generation. Beam search, simply put, select the text that maximizes the model's probability um, with some approximation. But essentially, it is what's called a maximum a posteriori estimate, um, which is the inference algorithm in machine learning, which you select the hypothesis or output that maximizes the model probability. So it's kind of believing in the model. So that's what people are doing in until like 2019. However, sequences with the highest model probability is often a bad sequence. That's what people realized in that years, and oftenly the highest probability um, is given by an empty sequence in machine translation. That's what people found, which may not be true in recent like LLMs, but it shows that the model probability is good indicator, but it's not something to be like blindly rely on. So that's what people found. So what we are doing, so what people found is that MBR decoding is a better alternative to beam search in several cases, at least. So what is Go doing? So let's say we have a picture of cat, and we have model. Instead of like sampling one sequence, we sample outputs randomly because you can do it in using a computation, so you don't need annotation. You can just do it at test time. So this is kind of free. And then you estimate the utility, which is, if you're not familiar with it, you can think of it like a similarity between the outputs using a function u, which I'm going to explain later on. So we have, say here, six outputs, and we compute the similarity between these six outputs using this function. And then select the output that maximizes the average utility to the others. So in short, it selects the one that is closest to all the others, which is point closest to the median or mean or middle, whatever you say. So you kind of sample a lot and then select what's in the middle. So kind of makes sense, right? So what we found, what people found is that MBR is awesome. It's better than Beam Search, and it's good, especially when the utility function is a very good one. So this is a work by Google Translate or Google Research. So what they found is that using BLERT, which was the state of the art at the year for machine translation evaluation metric, they show that it outperforms Beam Search by a lot using that utility function. So what they show is that the choice of utility function is crucial for MBR decoding. However, the problem here is that most of the utility function um, are trained to estimate the utility between sequences, not documents or paragraph or like longer text. So unfortunately for document level machine translation, there is no suitable way to compute the utility. So there are several works on doing that, but they're not applicable to MBR scenarios for various reasons. Okay, so what we propose is using optimal transport as a utility function. So let's say we have a sequence level, the sentence level utility function, and we have a document. Let's say for simplicity, we have a text one, I love cats, I love dog. That's very simple, but just for, you know, um, showing. So what we do is that we first segment the documents into sentences. So we have now 2 sentences for each text. And then using the sentence level utility function, which we know it works, using that we compute the utility between each sentences in the document pairs. And then compute the mapping from one one document to the other, maximizing the total utility, which in this case, if you map I love cats to I love cats, then that's the same text, so you get utility of 1, and in total you get utility of 2, which is the optimal, so that's what you get. So that is the utility of the 2 documents. So that's the definition. And so good thing about optimal transport is that for this example I showed for the same amount of documents, and basically sentences are kind of overlapping, but it can be flexible. Like you can have one sentence mapped into multiple sentences, or vice versa. Or you can have even a sentence that is not mapped to anything. So optimal transport is basically a way to compute 2 groups. So basically that's there's no constraints. So does it work actually is a question. We found that we tested machine translation, summarization, dense image captioning test. All of them are supposed to generate a paragraph length text, and we found that MBR with optimal transport outperforms MBR with sentence level utility function. Although I would say it's not like it vastly outperforming. I guess people are making it, making the utility function so that it can also be helpful for document level uh, metrics. So maybe in future we will have a utility function for document level things. That will be our hope. But yeah, so as for now, it's gonna be useful, I think. So optimal transport can extend sentence level utility function into document level utility function. And it is flexible, so you can, so for example, if you have a document level utility function, you can then combine them for like book level utility function. It is so flexible anyways. So, and MBR using optimal transport outperformed MBR in document level text generation tasks. So the future work is that, so optimal transport is slow. I should say MBR is already super slow, and optimal transport gonna make it even slower. So we have to think about the way to compute it faster. There are lots of work in optimal transport, so I guess some of them will be useful. And also the question is that there are hundreds of formulations in optimal transport. In this work, we only used like 2 formulations. So wonder what it will be the best, variation of optimal transport for text generation is undiscovered yet. And also, important aspect is that we only worked on English and Japanese in our experiments. So the optimal transport why it works is that it is kind of flexible with respect to the structure of the text or the document. So it may depend on how the documents are written in that languages. So it's unclear how it will work for language that is syntactically different from these languages, which unfortunately I only have a command over these 2 languages, so I couldn't work. So, but yeah, hopefully people can figure it out on my behalf, or yeah. So there are tons of feature work, but I think optimal transport is one of the interesting topic that we can pursue with MBR decoding. So I hope it will be inspiring to you to work on this one.